An R tree, rectangle tree, or region tree is a type of spatial data structure optimized for indexing multidimensional data, such as points, lines, rectangles, and polygons. It is particularly useful for managing spatial queries like finding the nearest neighbor or identifying objects within a given region. For more tech interview materials, please go to our website at bowsy8.com. Basics of an R tree. Definition. An R tree is a balanced tree, similar to a B tree, used for spatial indexing. Each node in an R tree represents a bounding rectangle that contains one or more data points or child nodes. Structure. Root node, the topmost node containing references to child nodes. Internal nodes, non-leaf nodes that contain bounding rectangles and pointers to child nodes. Leaf nodes contain actual data entries, e.g., rectangles, points, or references to the spatial data. Bounding rectangle. A bounding rectangle is the smallest rectangle that completely encloses all the data points or child nodes within it. How an R tree works. 1. Insertion. Locate a leaf node. Find the appropriate leaf node where the new data entry should be inserted. Minimize overlap. Choose the bounding rectangle that requires the least expansion to accommodate the new entry. Split. If a node exceeds the allowed capacity, e.g., for entries, split it into two nodes and propagate the split upwards if necessary. 2. Search. Traverse the tree. Starting from the root, check each bounding rectangle to see if it intersects with the query rectangle. Check leaf nodes. Once the relevant leaf nodes are reached, compare the data entries to the query criteria. 3. Deletion. Find the entry, locate and remove the data entry from the leaf node. Adjust bounding rectangles. Update parent nodes to reflect changes. Rebalance. If a node becomes underfilled, merge it with neighboring nodes to maintain balance. Applications of R trees include 1. Geographic Information Systems, GIS. Spatial queries. Efficiently query maps to find regions, roads, or landmarks within a specified area. Route planning. Quickly identify paths or neighboring locations. 2. Database systems. Spatial indexing. Used in databases to store and retrieve spatial data like coordinates or geometric shapes efficiently. 3. Computer graphics. Collision detection. Identify overlapping objects in 2D/3D environments. Rendering. Optimize rendering by determining visible regions in complex scenes. 4. Nearest neighbor search. Quickly find the closest data points to a specific location, e.g., finding the nearest restaurant or gas station. 5. Robotics. Pathfinding helps robots efficiently plan paths by managing spatial obstacles. Advantages are 1. Efficient spatial querying. Handles range and nearest neighbor queries efficiently. 2. Balanced tree structure. Similar to a B tree, ensuring predictable search and insertion times. 3. Dynamic updates. Supports frequent insertions and deletions without requiring a complete rebuild. Limitations include 1. Overlapping regions. Bounding rectangles and internal nodes may overlap, which can slow down search performance. 2. Complex splitting. Node splitting algorithms can be computationally intensive. Thanks for watching. For more tech interview materials, please go to our website at bowsy8.com.